this course or this video is part of machine learning course arranged at University of Vaasa. In this video we are going to explain or to give some examples how to use the artificial neural networks function, which was built in the course with simple functions, or it was built from scratch. It is quite simple code. It works under Octave or under Matlab. The function is not very efficient in terms of speed, but still it can do the required basic like functions or tasks. So this is the function. It is quite easy, quite simple. And in order to test this function, of course, you can use this function to prepare your report in the course, and also you can use it for some other purposes. Of course, there are many more efficient like codes or functions in under MATLAB or Python or some other codes, but still this as a simple designed function where you can go inside and also you can modify and you can test different ideas here, which could not be available in other ready packages. Anyhow, let us start with simple, quite simple application, and then we go and we test different situations. Okay. Here I will assume that we have a data, for example, database or whatever, Excel file, for example, with 5 inputs or 5 attributes, and we have 1 output. And our objective is to capture or to learn the relation between the inputs and the outputs. So we will design actually this relation, inputs and outputs. It can represent anything. So maybe, for example, it can be a health record, for example, where is the one input is the blood pressure, the second input maybe the hemoglobin, for example, and whatever. And it can also and the output, for example, can be the expected, for example, sugar in the blood, or some kind of other diseases, or it can be also data for diesel engine, for example, or whatever. Now the input X, I will assume that it is just random. And now I'm using Octave, and random N means that I generate a random distribution or random numbers with normal distribution, and I can use any number of samples. So here I can assume that I have 100 samples in the database or in the Excel file, and we have 5 inputs, so it is 5 here. Okay, so that's it. This is the input X. I can modify it, of course. I can modify it in any way that we want. And for example, you can use the third attributes if it is related to human, for example. It can be like male and female. So in that case, you can replace like male with some number and female with other number. For example, +1 and -1. So you can change your symbols to numbers. Okay. And the output, let us start with quite simple case, that the output is just linear relation with the input. So y is equal to, for example, the first X, so all columns, or sorry, all rows, first column, it means that this is the first attribute, plus 5 times the second attribute, so it is X of second, okay, minus maybe 7 times X of, okay, so it is all samples, their attribute, and maybe plus 0.1 times X all samples, fourth attribute, and finally minus X of last one is the fifth one. Okay, Now you can see that it is linear function. It is just linear relation. The output is linear relation with the input. Of course, in that case, since if we know that it is linear and we have 5 inputs and 1 output, then all what I need, it is not noisy, there is no noise, so all what I need is only 5 samples in order to solve this linear equation, is to find the parameters 1 and 5 and -7 and 0.1 and -1. But now assume that you don't know. You don't know is it linear or not linear, so we put it as very simple as in this shape. I will start without noise, and then we will add noise later. Okay, now I want to build the neural networks to solve this problem. Okay, so before that, let us see how it will be. So if the total data, X capital, is the inputs, consists of the inputs, which is X, and the output Y. Yes. So if you want to see how it will be, so we can show the first maybe 6 samples, okay, of the data. Sorry. Yes. Sorry. Yeah. So you can see this is X1, X2, X3, X4, X5, and this will be the output. Of course, X1 we have 100 samples here. Okay, now we build our neural networks. So as I said, we assumed in the beginning that we don't know this relation, and usually we start with as simple as possible of a neural. Then we if it didn't work, then we increase the complexity. Okay, now if we start with this is the function, as you can see it. Yes, this is a function. So it is W is weights, the output is the output, and then this is the function ANNmat, artificial neural networks for MATLAB or for Octave. Then we put X and so on. So I will call them here, for example, W and the output O, okay, equal to artificial neural networks mat. Okay, and then we put here X is the input and output, so it is X capital. Okay, and here you put the neural network configuration. For example, if you have multiple layer, I show you how to use it. You open this vector. Okay, so if you put, for example, 1, 2, 3, 1, what it means? It means that you have one neuron in the input. So this is the first layer, and in the hidden layer you have second layer with 2 neurons. In the third hidden layer you have 3 neurons, and the output is 1 neuron. Remember that the number of neurons in the output must be the same as the number of outputs in your data. Here in our data we have 1 output, then we should have only 1 neuron. So I will start with only 1 neuron only with a linear function. The second thing that or the third thing that I should need is the functions, because we have several activation functions. So we can use linear, we can use rectifier, we can use sigmoidal or tanh function. Okay, so I will assume that here we use only linear function. Okay, and the fourth element is the error performance that you want to reach. So I will assume that I would like to reach 0.01 in the error performance during the learning, and the maximum number of epochs before the learning stops, so we can continue until 200 of iterations of the learning process. And then final one is the percentage. It means that what is the percentage used for the learning, and the rest should be used for the validation. So we will use 50-50, 50% and 50%. Okay, so let us see how it will work in this case. Yes, actually it has captured completely the relation. So you can see this is the error. Here is the error. So the error goes to 0, and in the validation you can see they are actually identical. So you cannot see 2 of them because they are identical. So the neural network has converged the perfect relation. Okay, so it has solved the problem in 3 seconds, and it has achieved this 0.01 error. And if you want to see the weights, you can put just W, and you can see that actually, because the first weight is this is the offset, so the offset is almost 0, and the first weight is 1, so it is, as we have seen, yes, it is 1, 5 minus 7.1 minus 1, so you can see them. So it is 1, 5, almost 5, and this is minus 7, it is minus 6.99, and this should be 0.1, so it is 0.09, and this is minus 1, which is minus 0.99. Actually, we can say that our neuron has captured the relation very fast and almost perfectly. But again, this is not a big issue actually, because we know it is very easy to solve. Now let us change a little bit. So what I'm going to do here, I will add noise. Okay, so I will add some noise like random, normal noise, and so it should have the same number of rows. So it is 100 and then 1. Okay, so now maybe this noise can be large, of course. It has mean equal to 0, but the variance equal to 1, so the noise is high. But let us see what will be the effect of adding this noise to our data. Okay, now I will repeat the same learning, but I need to update the input data. So x and y, as you can see, x and y. So because I updated y, so I need to update this function. And finally, I repeat the learning. Yes, let us see what will happen now with using linear. Yeah, okay, it still works. Yes, it still works, but now you can see there is some difference, as you can see it here. This is for the validation, by the way. This is the output for the validation. This is the output that was not shown to the neural during the learning. So this is the rest of the data, because we divided the data like 50 for learning and 50 for validation. So for the validation, is still the neural is able to follow at least the general of the signal. So it works fine. But the error, you can see now, the errors cannot be 0. This is the minimum error that you can achieve here because of the noise, because of the noise. Of course, as you increase the noise, then the problem will be even worse. Okay, so far so good. Now let us see what happens if we because the relation now is linear, as we can see, and if you use larger neural network, more complicated like configuration of the neural networks than needed. So what I am going to do here, so what happens if we add like 5 neurons in the first layer and 1 neuron in the output layer, and then we use like tanh function, activation function in the input layer, and linear in the output layer. So now we use, let's say, if we make it even more general or more complex, so we have 10 neurons in the input layer and 1 in the output layer. And now we use actually more than needed, because the relation is linear, and we used like complex nonlinear neural networks to learn or to try to capture the relation of between input and the output. You can see, of course, it takes longer time, and yeah, it works, but it is worse actually. You can see in the validation is worse than the linear case, even in noisy case. And the reason why it is worse, because now we have like what is known as overfitting. We have overfitting, so we have more complicated model to model simple model, to modeling a simple data. So in a simple relation. In that case, we have overfitting, where you can see the error is clearly is much larger than in the case of the linear, and it takes longer time, more resources of your computer, which is not needed. Okay, now let us do something else. So instead of using linear, Now I am going to use like nonlinear inputs. So divide this video into two parts, every part about 15 minutes. Okay, now as I said in the first video that we like to have now nonlinear relation between the input data and the output. So this nonlinearity has been given in this way. So of course you can think about it. So but what I did here, that I just multiply the first attribute and the second attribute minus 7 times the absolute value of the attribute. I didn't take into account the sign, so if it is negative it becomes positive and so on. So and plus 0.1 times the fourth attribute, I take square of the fourth attribute. For the fifth attribute I take cube. Okay, and maybe we say plus 5 times maybe the sign of, let's say, the first attribute again. So it is 1. Okay, and plus noise. Okay, so what this means that sign here means it takes only the sign of the input. So if it is more than 0, it gives plus 1. If it is less than 0, it gives minus 1. And you multiply this by 5. Okay, and then we have plus this additive noise. So this is now our data. So our data becomes highly actually nonlinear. Okay, and so now we update our input. So we have x and y. Before that, I like to see what is the maximum value of y and the minimum value of y in order to know how many neurons. Okay, the maximum of y is 17 and the minimum value of y is minus 24. It is okay, not that big. Okay, yeah. Let us start with using the same configuration of linear neural networks like we did before. Yeah, so this is for the linear case. Okay, and we use one neuron with linear activation function, and let us see how will be the result. Or is it possible to capture the relation with linear? Okay, now you can see that the error is large. Okay, the linear relation is still somehow is taking the same trend, actually, the same trend of the data. So it is like averaging the data. You can see somehow it is not, of course, averaging, but it follow the trend of our data. Even the actual data is this red one, and the blue is the output of the neuron. Remember that those 50 output are for the validation, so it was not shown to the neural network. Okay, and this is the error. It looks that the error is small, but remember here the number, maybe it is not very clear. I can put zooming here to see. So the error actually is close to 4. The error is close, more than 4 actually, the final error. So it means that the error is large, the error is high. Yes, it can be shown here. So the average error is 4.4. Okay, so what means here? It means that our linear assumption didn't work. It was working perfect when the relation was linear, but now we have nonlinear relation, and the linear assumption here doesn't work. Okay, what can we do? Let us start with increasing the complexity of this network. So I will use like 3 neurons in the input and 1 neuron in the output. So we have 2 layers now. Okay, and the first layer I will put tanh function, and in the output layer we use still linear function. Remember that if you use like tanh function in the output, the tanh function gives the maximum 1 and minimum -1. But here, as we have seen, that the data is 17 and -24. So if you put tanh function, the output, the error will be very high. In order that if you want to use tanh function, the best thing to do is to normalize your data. So you can take y and you divide this y by its maximum absolute value. In that case, the data will be between -1 and up to 1. Okay, but in this case, because I didn't make normalization for the output, then it is better to use linear function. Okay, let us see how it works. So of course, I don't know if this network is enough to capture the relation or not, but let us try. You can see here that the adaptation rate is 10 to the power -3. Sometimes we increase the adaptation rate to increase the learning, but this can also cause some divergence sometimes. So okay, now you can see, so with this nonlinearity, the data is, I don't know if it is better than before or not, but at least in terms of the average error is worse. For the average error is taken over the learning, not in the adaptation. But you can see this is the average error, but actually it approaches better than before, because before it was approaching more than 4, but now the error is approaching like 2 point something, maybe 3 or less than 3 actually. So the error in terms of convergence error is better than the linear case, and this is for the validation. This for the validation. Of course, the data size may be not enough to capture all relations, because as we have seen here, so we have this sign takes only the sign of the data is something highly nonlinear, and also we have this absolute value. Also it increases some nonlinearity, and of course we have the square and the cube and the multiplication, but still let us try with a little bit larger network, maybe with 5 neurons in the input, and maybe we can increase a little bit the data in the training, so to 60% instead of 50%, and let us see how it will work now. Yes, it takes some time. Yeah, so still not very good, but somehow it can follow actually much better than before. Not perfect, so we cannot say that it has generalized the data, the relation very well, but it works. And if you compare to the error now, you can see, so the error is even going to be better, and actually if we increase the number of epochs to be more than 200, maybe it will converge even better. So this we can do actually. So if we add the epochs, but it takes time, of course. As you increase, it takes more time, but I should say here that I am running now this Octave over somehow old computer, and this could be one reason for that slow, and it takes that much time. But if you run it over a faster computer, or if you run the same code over MATLAB, actually when I tested over MATLAB, it was more than the time was even almost half the time required here. So you can see that when I increase the number of epochs, so the convergence becomes even more, and the data actually there is not that big improvement in the validation part. Not that big improvement, even in the convergence becomes in the training part becomes much better, but in the validation is not that good. And okay, what happens if I change? Let me to keep time. I don't want to have long time waiting for the result, so I reduce the time to 100, and let me also reduce the data to 50%, so only 50 of the data used for the training. And but instead of tanh, I use rectifier function for the input. Okay, and let us see. Rectifier function is almost like linear, but it adds some nonlinearity because the data is defined only for the positive side. Okay, so it works. It works better actually. It can work better. So, but it still is not perfect. And what we can do. Let me try also sigmoidal function again. Okay. Now I'm just showing you how can you use the function. So yeah, it works as well. So what else? So I can use tanh function, but but now I will little bit increase the adaptation rate to be 10 to the power minus 2 instead of 10 to the power minus 3. Okay, and let me see how this will affect the results if we increase the adaptation rate. Okay, you can see here now. So actually, I think maybe there's something here that is not good, but most of data actually was. And remember, there's noise also. So maybe this part, for example, maybe due to the noise. But otherwise, actually, I can say that now the neural network has captured the relation, and actually the error here, you can see that the error is not that good, but in the training, okay, of course you can do many things here. You can increase even more. You can use, let's say, 10 neurons in the tanh function, the input, and then output is one layer. But remember that when you increase it too much, then you might have like overfitting, and then the error can be even large. So you can see now, yes, most likely that I have overfitting now of the data, yeah, and so on, yeah. So, but you can see also the errors is 3.8. So in the learning part, the error becomes less. Okay, so the error becomes less, but in the validation is worse because of this is one sign of the overfitting. Okay, now let us go back to the maybe we use 3 layers. I show you how to use 3 layers. For example, if we use 3 neurons in the input, 3 neurons in the hidden, and 1 neuron in the output, and then we use like tanh function in the input, rectifier function in the second layer, and linear function in the output, and let's see how it works now. Of course, we will have more. So this will be the result. It is fine as well, but actually it has captured almost all trends of the data. Okay. However, we have strange error performance. So the error was somehow strange because when we use actually multiple like layers in this way, so we can be like trapped in any of this local minima. This is the reason that we use deep learning when we use many like hidden layers. Okay, let us go back to the simple case. So for example, maybe 2 neurons in the input and 1 neuron in the output, and maybe tanh and linear. But let us see now how it works. And then the last thing I would like to show you is what happens if we increase the data or the adaptation rate much more. So this is the result. Okay, so now if we increase the mu, let's say 10 to the power minus 1, what happened? Okay, it is still working, as you can see. So it is, I'm not talking about performance now, but it works. But what happens if we put it like that, mu equal to 1? Okay, this is the maximum that you might get. But now what we have, none a number. What means none a number? It means that the algorithm has diverged, so it will not reach to anything. So this is the dangers of increasing the adaptation rate. So increasing it can increase the learning, but also you may get in divergence situation. So maybe 0.01 or 0.02 is good. Actually, the adaptation rate itself, it can be adapted. So we may increase with some small number of the adaptation rate, and as we are closer and closer to the solution, we can like post this adaptation rate to be higher. So there are some algorithms in order to optimize the adaptation rate, but those algorithms are not implemented in this function. Okay. Again, so we can now use 4 and so on. Actually, this is the purpose of this video, is to show to you how can you use. You can see now it works. So you can, for example, if you have any data, for example, if you download some data from the World, for example, Health Organization, you can find data about different diseases with attributes and certain output. So you can select one of these of the columns as your output and the others as your input, and then you can try them with this function and try to capture the relation. Sometimes it can be hidden relation between the inputs and the output. You can also find some, if there is some correlation, for example, if you remove one of the data and how this will affect the learning, for example. Yes, that is all about this video, that how to use ANNmat. The function itself is available on Moodle, and if you don't have it and you like to try, you can just send me email so I can send you the function, so you can you yourself you can improve this function, or you can develop this function further. But again, as I said, the purpose of this function is not to solve complicated problems. Even you can use it for any configuration of neural networks, but still the purpose is just to learn how it works and how you can use, as I said, that you can see, for example, you can try different adaptation rate algorithms, for example, or you can use different functions. For example, instead of tanh, you can, if you like to use some function which is not standard, this code gives you this opportunity to try different algorithms. Thank you very much for watching.